So welcome. It's post-lunch session. I hope all of you are awake. So today we are going to talk about a couple of machine learning problems in our search ads business and how we have gone about solving those problems. We will talk about some of the solutions that are available in the open source world from Google. So some of you may already be familiar with some of those solutions. So before I get down into the problems that we encounter and how we go about solving them, I'll start with providing a very, very high-level overview. Think about it as a 30,000 to 50,000 feet overview of how our ad serving systems work. And we'll go down into the specific problems that we have solved. We're basically going to use case studies in order to talk about the examples. One request I have is if you can hold off your questions towards the end. Sugato and I will try to leave 10 minutes towards the end of the presentation for you guys to ask questions. So if you can hold off your questions towards the end. So just to set the terminology straight and just to get everyone of us on the same page, this is a very, very high-level overview of what the system looks like. We have two sides to the system. On the one side in our system, we have advertisers, and on the other hand, in our system, we have users. Advertisers add content to our system. That content is called creatives or ads. They have an interface through which they can add these creatives to our systems. They go into a database on our side and basically are kept there. Users, on the other hand, when they are looking for something, they send to us what is called a query, a search query. They type the query. They can either type the query in the search box. Everybody is familiar with it, I hope. Or they can basically do a voice query with the new assistive technologies. So what happens is when a user does a query, the query gets sent to both our search systems as well as ad systems simultaneously. Search systems go and do their magic. They'll produce the organic search results that all of you are used to seeing. Similar, at the same time, ad system basically receive the query as well, and they do their magic, their side of the magic, and present commercial results to that. So we are also going to look at what points in this flow do we end up using machine learning technologies. So we get a lot of content in our systems on a daily basis, on a regular basis. It's just not humanly possible for us to evaluate all that content manually. There is definitely, as we are making the systems open, there's definitely potential for receiving content that we don't think is right for serving to our users, whether it is because of policy reasons, whether it is because of regulatory reasons. We also want to be able to classify that content. So we apply a lot of machine learning technology there, which means when advertisers add their creatives, they are evaluated using machine learning technologies. We basically label them for policy violation, and eventually the stuff that is clean or the content that is clean makes its way to the next stage of our system, next stage of the flow. So even after cleaning up all the content, even after making sure that everything is sanitized, we still have a lot of content in our system for a given query. So there is definitely a lot of need on our side to basically select the right content, which when we receive a query, select the right content that matches the query, that is relevant to the query. Even after we have selected, let's say, hundreds of creatives out of all the bigger set that we had, we need to rank it. Which one is the best satisfying the requirements of a particular query? And once we have ranked all of it, again, because this is the ad part of the system, there is a pricing component involved. We're not going to talk about any of that. But this is sort of just a very, very high-level overview. And the reason is to set the context for the case studies that are going to follow. So on a broad level, what kind of data challenges, what kind of, let's say, machine learning specific challenges do we tend to encounter in our system? Because of the diversity of problems that we deal with on a daily basis, there are diversity of challenges that we encounter as well. So we have challenges on the data side. Sometimes we have problems that have a lot of data, and the challenge then tends to be, how do I train models in a reasonable amount of time with all this data? Or if I do want to subsample the data, what is the right level of subsampling and what is the right technique for subsampling that data. Or when I have built the models, how do I serve those models basically at scale? We also have cases where we don't have enough data. In those cases, how do I augment the data? If there are techniques for augmenting the data, human labeling tends to be one of the techniques that's used. But again, if we want to get to an even bigger scale, human labeling itself will not scale beyond a point as well. So we start falling back over to modeling technologies. Should I use transfer learning in some of those cases? Do we have pre-trained examples from another domain that I can basically leverage in this case? On the modeling side, our engineering teams are always evaluating better, more advanced modeling techniques to do a couple of things. To basically train faster, to get higher accuracy, more generalization, and to be able to serve using fewest amount of resources possible, right? So there are challenges on the modeling side as well. As the engineers are evaluating different modeling technologies, we need to figure out that we need to ensure that our infrastructure keeps pace with it. Last but not the least, we need to we need our models to be explainable, free from bias, and all those things. So we invest in a lot of those components when building the models as well. We finally obviously want to be able to serve those models to eventually provide a good experience to our users when they come to our products. So what I'll do now is we have 3 case studies lined up. I'll talk through the first 2 case studies, and Sugato will talk through the 3rd case study, and we'll basically try to give you a flavor of what kind of challenges we saw in those case studies and how did we go about solving them. Just a very sort of like overview of that. So our first case study it came from an insight, and the insight was we saw that in our system, our advertisers are having to spend a lot of time creating content, which is the creatives. And they are tuning and retuning things. They are manually doing a lot of work. They are testing, and they're spending a lot of energy doing this work. And the insight of the thought process that happened on our side was, given that Google has developed translation technologies, machine learning technologies, is there a way we can use these technologies to help our customers, which in this case is advertisers, right? What it also, the second part of the thought process also was, given that we'll make these technologies available to all our advertisers, not just a few of them, it sort of democratizes, it sort of levels the playing field for them as well. So the result of this sort of thought process building was a product that we call as responsive search ads that we announced in the Google Marketing Live in July of this year. And what the product does is, in order to reduce the burden on the advertiser, we basically say, you don't have to keep tweaking or modifying your creatives every day. You give us some seed content, and this is just a starting point, and we will figure out what are the right combinations that we need to generate in order for you to meet your needs. Our algorithms basically look at the content, combine the content in algorithmically, and then score the content, and then basically surface the most relevant and the most performing content in the system. What we do as a result is we obviously take away the burden from the advertiser. We take away the churn that they have to otherwise go through on a regular basis, but we also just discard a lot of content that is not needed from our systems. Okay, so you can say, okay, what kind of challenges did we run into in this particular product? The first challenge is we have no exact training data. Our learning systems that predict, let's say, either the quality of a creative or click-through rate of a creative had never seen some of those combinations before. So how do our systems figure out which one is the right content to basically surface? So in this particular case, we went, the initial solution that we came up with is, in order to train our models, we basically went with human labeling. We created very extensive guidelines for human labelers to go and label the content. But again, human labeling can only do so much. But that was a way to bootstrap our models. The second challenge we ran is the product is launched in multiple languages. It's not just English. There are tail languages where there isn't enough content available in those tail languages. So the way to solve that for us was Google's own translation technologies. And that was the initial insight, as I talked about. So we are using Google Translation, which basically uses sequence-to-sequence modeling underneath to translate the content from various other languages into English language. Because for English language, we do have the label data. We can basically sort of bootstrap from that point onwards. But again, it's not as if that we could use the translation models as is, primarily because a lot of those translation models are trained on long-form content, and they were trained for a very different vocabulary. So some of these models had to be retrained for short-form content as well as a very different vocabulary. But I'm happy to say, yes, we were able to do that. Finally, the product actually worked in tail languages as well. On the modeling side, there were a couple of other challenges. We wanted our models to learn that putting redundant content is not a good thing. You can't have two sentences effectively saying the same thing. Something like, let's say, free shipping or get shipped for free kind of thing. That's redundant information. There's no additional information in that two pieces of content that we had. So there are modeling related problems that we solved like that. The second problem was a lot of advertisers had very different preferences. Some would want their brand information to be in first part of the sentence. Some would say, I actually want shipping information to be, let's say, in the first or second part of the sentence. How did we basically ensure that our models learned those preferences? So again, we got some label data to bootstrap the model, and from there the models learned that, this different set of advertisers have different preferences, and we also basically give suggestions to the advertisers if their preference is probably not resulting in the right performance. We also give feedback to them. And as I said before, explanation of the model behavior is extremely important. We need to be able to reason about what the models are doing and why, because it's basically for two reasons. One is to both build intuition, but also to debug these models if there is a problem at some point. So these are some of the challenges in this particular example that we ran into. If I switch over to the second case study that we had, and the goal here is, let's say, to identify ads that we considered as egregious. And egregious means really, really bad. We really don't want to show it no matter what. But remember, in the beginning I said we filter out the ads for policy violations and things like that. These are not policy violating. Like, the content is not policy violating in any way, but really it's really not good. So at Google, we basically optimize for user experience, and the thought process is if we optimize for user experience, all else will follow. So let's say for a second we didn't do that. And this is a completely contrived example. Let's say we simply said, oh, whatever the advertisers are going to give us, we are going to basically show it, right? And I've basically created a very contrived example here where user is actually looking for, let's say, furniture with cherry veneer, but advertiser said, anytime somebody says veneer, just show my ad. And let's say we do that, right? We don't want to do this. But how do we, because we don't do this, how do we tell our system, or how do we tell our models to learn that this is something that they shouldn't be doing? So what happens is every query and ad pair for us tends to be unique. And you can imagine what kind of data slicing challenge that is. If we have to learn something about each and every query ad pair, it's just not possible. Not only is it not humanly possible, it's not even possible for our systems to learn at this level of granularity or this level of slicing. So obviously we think in terms of aggregation, but we also think in terms of building human labels for a lot of these problems. But again, human labeling can also scale to a certain extent. And this is one problem where we basically leverage transfer learning. We fell back to this technique where we are saying if there is an already pre-trained system or a module somewhere trained on a similar problem domain that we can leverage for this particular domain, maybe retrain it a little bit and so on, and then we can apply that. There are two ways you can do transfer learning. There is a tool called AutoML. If you go to cloud.google.com/AutoML, you can basically we go sort of read the documentation of the tool. But what the tool allows you to do that is it allows you to search for network architectures that meet the requirement of your problem domain. And it'll actually even train your models. It'll find those modules. It'll sort of pick up those modules for you, and it'll train those modules on a smaller set of data. If you are somebody who wants to sort of look under the hood a little bit, try things a little bit yourself, you can also look at TensorFlow Hub. TensorFlow Hub is an open source repository of pre-trained TensorFlow modules, and we'll talk a little bit about what those modules are, that you can basically, where people can publish, search, or consume pre-trained modules. So you can basically go to TensorFlow Hub repository. I'll take a minor detour into TensorFlow Hub just to give you a flavor of what is possible. So when people think about building an effective machine learned model, there are 4 key ingredients that are needed. You need a learning algorithm. So stochastic gradient descent tends to be the most common one. You need a lot of data, a lot of labeled data. You need compute power that basically can run those algorithms, and the algorithms can basically churn through that data. And you need modeling expertise, people who can look at what the learner is learning and whether the learning is going in the right direction and what kind of tweaking that you need to do in order to make it go in the right direction. Right? That is a lot of sort of components to get your hand around, especially if you are just starting out on machine learning. So Google had this thought that this is a complex space. How can we make it easier for people who probably may not have access to all that compute or may not have access to all the data, and make it really easy for them to come build machine learn based solutions. So we released this open source tool called TensorFlow Hub. And TensorFlow Hub, what you can do with TensorFlow Hub is, if you are a consumer, if you are looking for a module, you can basically search in TensorFlow Hub you can define your problem that, oh, maybe it's a natural language based embedding that I'm looking for, or I'm looking for, let's say, a problem where somebody has ranked results in a particular search-like space, and you can find the network architectures that exist that people have already uploaded, and you can pull that architecture as part of your model. So TensorFlow Hub has something called modules. And what a module is, it's a pre-trained TensorFlow graph. Somebody else who probably had a lot of data or who probably had access to compute information has trained part of their network, and they have basically composed it in form of a module. They publish it to the TensorFlow Hub repository, and they've uploaded it for people to use. So if you have a similar problem, you can basically go and search TensorFlow Hub. You can, not only can you pull just one module, you can pull multiple modules as part of building your own network, as part of building your own solution. Modules are reusable, they are retrainable. You can probably basically pull modules, generate a new module out of it, and upload it back into the TensorFlow Hub. So coming back to the problem that we were talking about, the problem was we wanted to identify bad query and add pairs, and we didn't have enough data to be able to train the models. So we did what anybody of you could do with TensorFlow Hub, which is we went to the TensorFlow Hub repository. We have an internal repository. We went to the TensorFlow Hub repository. We searched for modules, pre-trained modules that were trained on a larger corpus of data, were similar to our problem domain, and had good results. So we found one. We imported that into our network. We trained our network using that and produce an output. It's something that is deployed in our production system, works really well. The one thing that I want to mention with respect to TensorFlow Hub modules is you can pull a module and retrain the weights if you want, or you can decide not to retrain the weights based on your data and just basically integrate it as is. In our case, we incorporated the TensorFlow module as part of our own deep network that we were building and trained a model that is currently deployed in production. It's performing really well. So the caveat with TensorFlow is, or with TF Hub is, you can pull modules, but then you end up pulling, you have to be mindful of the fact that you are pulling, let's say, either modules or embeddings. If you're pulling embeddings that are potentially pretty large. Yes, large embeddings will give you a model that is more accurate because you have more data to play around with, but you'll have to think through your own serving situation. How do you go about serving it? In our case, we ended up making tweaks and changes to the model in order to bring it to a shape where we had a good trade-off between serving and basically the accuracy of the model. So this is what this graph is trying to depict. I mean, we don't have to go into the details of the graph, but just to think through some of these challenges. So with this, I'll hand it off to Sugato, who will talk about the next case study.
Thank you. Can you guys hear me? Great. Thank you, Sunita. So I'm going to talk about the third case study over here, which is performance attribution. So, as we see in many cases, language really matters. So I'm going to start off with an example given by an esteemed colleague of mine at Google, who quoted this, thing from Winston Churchill, who was known to be a very master, gifted wordsmith. Some of these words actually took people to battlefields, and ads are no exception. Of course, hopefully with not the same end result. So let's take a look at these two examples. Again, these are contrived examples. These are just to illustrate the point. So on the left side, you see a particular ad from cozymeal.com. And on the right side, you see another ad from cozymeal.com. Now suppose I ask you, which one do you think will be more effective? Should the advertiser use the one on the left or on the right? I can see some left, some right, and I think the conclusion is that it is a difficult proposition, right? It's actually something quite tricky because you don't know which is, for some of you it might be appealing to have the best cooking class, for the others it might be appealing to have, San Francisco best chefs. It's unclear. And it turns out that, the nuances are such that you really have to now take a look at the data and do some modeling. And oftentimes, we also end up personalizing it for individual users. But right now, let's just think about a kind of a model which is across all users. And, if you take a look at the historical, literature in this area, there's been a lot of work done in this area. Starting from back in the 50s and 60s, there have been people talk about good copywriting principles for ad copyrights, all the way to having, logistic regression models fit to this, something which starts looking at mutual information. Like for mutual information, you can say that, let's say we have a bunch of words, and we have the good and the not so good class. Which words are predictive of good versus not good? And you can frame this as an information theory problem, calculate mutual information, and all the goodness follows from that, right? You can also fit, L1 regularized models using Lasso, and there's bunch and bunch of, papers. But the bottom line of all of these papers is that they do some sort of counting, some sophisticated counting, regularized counting, information theoretic based counting. So on the right side, what you'll see is top performing. This is kind of taken from that particular link, but these are the top prominent words. So it will kind of tell you which are the words which lead to higher performance. Now, we applied that same technology over here, and here's what we got. Let's take three verticals: apparel, houses, and jobs. Take a look at these examples for a while. Do you see anything interesting over here? Right, you'll end up seeing a bunch of brand names. So on the apparel, you see, oh, Nike is good, Gap is good. On jobs, you'll see that Monster is good. Now, this is maybe interesting information, but what does it do to an advertiser who is not Nike or an advertiser who's not Monster? It's difficult for an advertiser to go ahead and change their brand name. It's easier, easier for them to, slightly easier for them to actually go ahead and change the price. But if you don't have a 50% discount, how can you advertise on your ad that you have a 50% discount? So I think the key insight that we came across was the fact that there are certain words which are difficult to modify. If you're an advertiser, for a particular brand with a particular, campaign, we cannot go back and tell you that, change the brand. This is going to be really good. Or we can't tell you, give a 50% off. This is going to be great for you. So we have to deal with those as the confounders. And we have to say that these are the confounders. I cannot tell the advertiser to change them. Instead, what I really want to do is to identify the words which the advertiser can change. Can we find those? So that was the basic tenet of our problem. So to illustrate the example, we have this cartoon figure over here. Again, kind of a cloud of words. Brand-related language would be Google and Pixel 2. Great performance, great click-through, but we don't want that. What we want are the ads on the top right, where they are not the brand-related words, but they are still the dominant words from that word cloud, which actually lead to better performance. So I think the rest of the talk, I'm going to focus on two methods that we developed for solving this problem. One is a mode of a direct method, is the direct residual selector method. I'm going to talk about that next, like at the end. The first one is a little bit more involved. It's called the convolutional adversarial selector. And both of these things we just published very recently. That's the name of the paper. The bulk of the work and the heavy lifting was done by a very smart intern from Stanford University, Reed. And he and Kazu are right now at the EMNLP workshop in Brussels presenting this work. So again, to recap, our problem statement is that we want to find the text that predicts high or low click-through rates, and we want to find out those words which are not affected by the advertisers. These are the confounders. So with that in mind, let's go to suppose you were given the problem today. What would you want to do? Okay, what would you do given the problem statement? What's the first solution which comes to mind? Well, suppose we have a lexicon of words. So our inputs are like this. We have the ad text, we have the confounders, and we have the click-through rate. We know whether it's high performing or low performing. And then we say that, okay, I have a lexicon of words, and I really want to find out which are the words which lead to high performance from this lexicon, right? So the first thing that you might do is to build a linear model. Let's call it LMC. And you want to predict the performance of the confounders, because that's the baseline. You take all the brand names, all this free shipping kind of stuff, those are the confounders, create a model. Then you add your lexicon to it, and then you train another model, and then you basically take a look at the delta between these two. So that's kind of the fundamental approach that somebody would take as a direct approach. And as I said, there's two techniques we have. One is the adversarial, the second one is direct. The direct one is closer to this approach, right? So that is almost like what you do on the first day that you look at this problem. Train LMC, train LMCL, look at the words which are at the diff, and then that gives you your high weight words. Let me for a moment tell you of a different view. So ignore all the connections and the complication. Let me kind of walk you through, and by the way, in the following slides, I'm going to walk you through every step of building the network. So this is just a sample of the overall network to give you a view of what this is doing. So two sides to this slide. Left side is the training process, right side is the inference process. On the left side, what we have is text coming in as input. Usual neural network encoding. We take text which is in a high dimensional space, encode that into a dense space. So that's the encoding block E. Then we do some feature transforms that we call convolutions. And for those of you familiar with the image processing, computer vision literature, you'll find this very familiar. Convolutions are kind of bread and butter in that community. Then we do some pooling, and then we pass through and train two sides of the model. On the top one is, as you see W soup Y, and on the bottom one is W soup C. Y is the variables we care about, C is the confounders. What are we doing over here? We are basically saying, let's split all the words into the confounders, because we know that that's the one at the bottom, and the one on the top are the variables we care about. And for those of you who know generative adversarial networks, GANs, or domain adaptive networks, DANs, this will seem familiar to you, because what you do is, on the adversarial side, which is the bottom part, you don't want to train on that. So you have this thing called the gradient reversal. When you do backprop to train the model, you actually flip it. That actually says that do not let the model train on this. Let it focus on the top side, right? So I basically am giving you the overall picture just to give the guiding principle of what happens in many, many adversarial networks, GANs, DANs, and so on, and ours is just a variant of that, is that let the model do the encoding, do some feature transforms, then try to figure out what are the words which are dominant without focusing on the words which are not. That's the negative part of it, right? And then at inference time, what we end up doing, I'll go into the details of that also, we have, pass it through the model, identify the words by running the inference of which are, causing high CTR versus low CTR, right? So that's kind of the overall view. Now, let's get into the details. The first step is the embedding step. That was one on the lower left. Suppose your phrases are Google Chromecast, simple setup, streaming environment. What we end up doing over here is the standard technique of encoding in neural networks. You take a high dimensional word space and one hot encoding, and then you kind of do this transformation to put it into a dense real vector, because neural networks internally handle dense real vectors, right? Now, we do convolutions for a very simple reason. There are certain times that you want to tokenize and just get single terms, like for example, bird. There are certain cases where bigrams are important, like for example, Menlo Park. And there are certain cases where trigrams are relevant, like New York City, and so on and so forth, right? So what we do is we capture all those unigrams, all the bigrams, all the trigrams, and we use that as features. And then the way we do that, we do the convolution of pairs, of triples, and so on, and pass it to the next layer. And the next layer, what it does is this notion of globally average pooling. Again, taking ideas from computer vision literature, what they do is once you have the convolution operation going on, you want to find out what is the average encoding. So you can do max, you can do average. Average is a very simple operation. It kind of tells you that if you have a big sentence, if you do pairwise phrases and you come up with the encoding, the sentence encoding is the average. It's just that. It's nothing complicated there. Now let's go back to our original picture. We have the 1 gram encoding at this point. We have the convolution giving the 2 gram encoding, 3 gram and 4 gram. And then we end up taking the final encoding, which is just a concatenation of those, right? So at this point, what we have is we had our input text. We basically encoded that into multiple levels of n grams, came up with the equivalent representation. And on the right side, E is basically our big embedding vector, which contains all this information, right? So that's the transformation that we have done over here. That's the transformation, which is that E vector you see over there. That's the E vector which gets in the right part of the network. And now on the right part of the network, as I told you, we have a standard DNN stack for learning the weights and for taking the negative of the confounders. The details of the math are in the paper, but essentially what this ends up doing is learning a weight vector for the confounders, learning a weight vector for the actual variables of concern, and making sure that the confounders are negated when we do the backprop. So this is just to show that, during inference, we now go ahead and follow a particular principle, which is again, if you recall, I told you in the image processing and the computer vision literature, there's a lot of related work in this area. So the top example is something that, you might say that you have the image, you have a bunch of these convolutional layers, and at the end of it, somebody is wanting to figure out that what is the dog. Suppose the thing is figure out the dog in the picture, it's an Australian Terrier. Now what happens if you look at like GradCam or certain other related papers in that area from the computer vision literature, they take the activation maps which come from the convolution layers. It basically says that which layer had how much activation for which part of the image, and they process that by doing some sort of a clever summing to figure out this heat map on the right. So if you see the heat map, the Australian Terrier matches to the the dog sitting over there, and essentially the terrier is actually the red dominant part, and then you can see the yellow around it to the blue, which is the background, right? So our goal is again during inference have something like this. We really want, once we have actually trained the model at inference, now you come and give me an ad, and I pass it through this, and I basically say, oh, these are the words which have the most importance, high CTR, and these are the words which have lower importance. That's our main motivation, right? So that's how we do this. We essentially take the maps that come out and we do a weighted sum of those maps. On one side we get the high click-through rate map. On the right side, we get the low click-through rate map. We do a binary separation. And again, the details, I won't go into the math, it's in the paper. But the basic idea is we want to identify what are the words which lead to the high click-through rate and what are the words which lead to the low click-through rate just by using the inference weights which came out of the network, trained network. So taking a step back, as I mentioned, we had these two methods. The first method I just talked about is the adversarial method. And the second method, which is a much simpler method now, is the direct residualization, right? And the direct residualization is essentially saying that, remember we first talked about LMC and LMCL. LMC was the one where build a linear model from confounders, and LMCL was add the lexicon to it and build the model, right? So that's exactly what we're doing over here. The bottom part, the bottom pipeline is basically LMC. It's the one which says, take all the confounders, the brand and the URL, pass it through a simple feed-forward neural network. So we're not doing a linear model, we are doing something slightly non-linear, just a simple DNN stack. Take the prediction of the CTR and use that as the residual, right? So that's kind of the bias term. Now the top part of the network now takes the add text and is now learning on the click-through rate with the bias of the CTR. So it's actually learning the residual of the delta between what I got from having the confounders predicted versus the original, right? Does that make sense? It's because this is standard residual error saying that, okay, I have one predictor, let me see how best I can do, take that prediction, use that as the residual for training the bigger one, right? So that's exactly the idea that we use over here. The bottom part creates the initial prediction of the confounders, and we want to train on the residual of that. This is a much more direct residual method. And inference also, we come up with the same idea. We have the high CTR map and the low CTR map. So at the end of the day, what do we end up seeing? I won't give any specific examples because, of course, there's sensitive data and so on and so forth. But what we see is that, at a high level, you can almost say that definitive words which convey information have high CTR, whereas lexical frills don't really give you a lot. So we'll get into some of the examples there in the paper, but if you categorize them. Oh, this is by the way the data set. We did run some experiments and we have some details of the data set. Again, the details are in the paper. We won't bore you with all the details. And when we actually did the experiments, I think we came up with an interesting measure of measuring whether a word is really informative or not. And let me try to explain the math on the top over there. So if you can see, the top one is just trying to say that, you have C and you have T intersection L, and the T intersection L are the terms in the lexicon. And what the top one is saying that if I were to make a prediction with all the lexicon words, what would be the variance? That's just computing the variance, right? And the second term is saying that what is that with the confounders. So this is just saying that how much reduction in variance am I getting by adding the lexicon terms. So if you can figure out two classes, and this is just a kind of an informative coefficient, and we have used that for evaluation of our methods. Some plots to kind of show you what happened. We have apparel, and we end up seeing that the high performing ads and the low performing ads have a separation. Of course, on the left side, you see that the separation is not perfect. There are some cases where you do see that the low performing is higher CTR, but in general, you see the trend. The higher performing have the higher CTR, and the lower performing have the lower CTR. So this kind of validates that, that when you identify these words as high performing, they actually contribute more to CTR versus the other way around. And we have some more comparisons to other, techniques. We had some older techniques, that Reed had worked on with his professor at Stanford, Dan Jurafsky, and we compared to those, and we did see that our lift improvement was better than the others, right? So it's all in the paper. But just to kind of close the loop on that, what are the kind of words which really, really worked well? Words which caused involvement with the reader, so which directly, reached out to them. Words which conveyed authority, and finally words which appeal to the sensibilities of the user. So these were the words, and again, just wanted to clearly highlight that this is not kind of a recommendation for any ad campaign of any sort. This is just for illustration. So these are all kind of canned examples, so just to convey the principles, not specific examples. Okay, so that kind of brings us towards the end of our talk. To recap what we did today, I think Sunita first talked about what we do at Google Ads, what are the different machine learning challenges we have, and then she presented how do we, the challenges in building a new product, and how do we identify egregious ads, and then I drilled down into the NLP research, especially performance attribution. This is our last slide. So basically, in conclusion, advertising is at the core of Google's business, right? We all know that. But what is kind of very, very important is machine learning, natural language processing, and all of these technologies are increasingly playing a very critical role. We are getting more and more of data, and as Peter Norvig, who's at Google, veteran at Google, likes to say, we always solve big problems. We all either work with millions of data points, or we work with millions of users, each having small data. So it's always a different sides of a big data problem. Requires a lot of data science, requires a lot of machine learning and expertise. And of course, there's still a lot of unsolved challenges to solve. So we are looking at you to help us do that. And just to put in a plug, we have our recruiting team who's here in the job fair and the trade fair. Do stop by, chat with them. We'll be here hanging out for a while if you need to talk to us. I think that's it. Thank you.